Hello, my name's Mattsi, and we're going to be doing another Screenkata in Rust today. We'll be doing a bit more of an algorithmic, more search-based programming challenge today. Now, you won't necessarily need to know a huge amount of Rust to follow along, but you'll need to at least know the basics. If you don't have a good understanding of ownership and borrowing, then you might struggle a bit, but as long as you've understood those fundamentals, you should be fine. And I'll explain some Rust bits here and there as we reach them. You won't need to know much about algorithms or search. We'll go through those as we get to them. And I think doing this more sort of search-based solution should be quite interesting. In terms of TDD, so test-driven development, I tend to use outside-in TDD to drive my solutions. But in this case, with more algorithmic programming challenges, that doesn't necessarily work too well, especially in particular in this case, because you only have one input, right? We just have this one number we're inputting into this problem to get some behavior out of it. But generally, what will happen with these types of problems is that if you have one valid acceptance case working, then everything else will pass. It's difficult to really drive the solution step by step in a problem like this with outside in, because you'll spend a load of time getting one test working, and then when that one test works, everything will work. So if you actually want to drive behavior piecemeal, one bit at a time, and have confidence in all the individual pieces, then you really need to do inside out. And I think that kind of comparison and that learning exercise is interesting, of knowing when to use one versus the other. But we'll get more into that. Don't worry if it's a little confusing. You'll see a demonstration shortly. So the n queens problem. This particular description, we've taken this from LeetCode. This is an old problem. I think I don't know when exactly it came into computer science use, but certainly I've seen it in some very old textbooks. But this particular example comes from LeetCode description, and they have quite a neat way of describing the input and the output. So they're using strings for the outputs. And I should probably start by explaining what the n-queens problem even is before I get into that. So the n-queens problem is the idea that you have a chessboard and you're only placing queens on it. And you want to place all the queens in such a way that none of the queens are attacking each other. So if you remember, a queen can attack in any direction, vertically, horizontally, or diagonally to any length as far as they like. So in this example here, this queen, I think, is in a valid placement because these two are not attacking each other. They aren't horizontally aligned or diagonally. And a valid solution for a board of size 4 looks like this. So the board can always change in size. So in this case, I'm using 4 as an example because it's a simple solvable case. But it could be, size 8 would obviously be a regular size chessboard, and you could have a chessboard size of 1,000 or something. And there are valid solutions to the bigger boards as well. I think I can't remember exactly what the biggest one that's been solved is, or whether there's an upper limit to it, but there are lots more solutions as the board grows bigger. You tend to find that bigger the board gets, the more solutions you find, and the more likely it is that there is a solution, because there are many that can't be solved. So, for example, if we have a board with one single cell, then that's easy. Just put a queen in there and that's solved, right? There's no other queen for it to interact with whatsoever, so pretty straightforward, that's solved. Then we have the 4x4. We've seen the solution for that. So it looks a little bit like this. And none of these queens are interacting with each other. None of them... Oh, wait a second, that's not accurate. Hang on. These two are diagonal of each other. I'm reading the wrong solution. Here we are. It's this one. So that one. Okay. So in this instance, none of them are interacting with each other diagonally, horizontally, or vertically. But you can also have a 2x2 board. And in a 2x2 board, there's no way to solve it because anywhere you place the second queen is going to be adjacent to the previous queen, right? There's no way to actually solve that problem. So how the heck do we go about solving this? Well, we have this neat little output here in which it's perhaps more obvious if I new line these. In which you have each string is a row of the chessboard. A full stop represents an empty space, and a Q, of course, represents a queen. And you can see one of the two valid solutions to the four-sized board here, represented in that notation. Now, it's worth just briefly mentioning the reason there's two solutions is really because this solution is actually an inverse of that solution. Pretty much any time you have one solution, you'll actually have two, because if you just flip it around, then it also works. Anyhow, so this is the expected output given for it should find these results. Place n number of queens in an n-sized chessboard, which is always square, in which no two queens can attack each other. You may return the answers in any order, and each solution should be a distinct board configuration with Q for a queen and a period, full stop, for an empty space. Okay, pretty straightforward. So what have we got to start with? We've got a function for n queens that takes our n input, which is just a number, and then returns a vec of strings. So that's going to return a two-dimensional collection of a number of rows. So you can think of this as a board, a vec of strings, as a collection of rows. It's one entire board. And then the vec of strings is all the boards that are correct solutions for this input n. And we have some acceptance tests over here, but it's blank right now. So one obvious test, starting with the absolute basics, is to say that if we, let's say, given n1, as we've discussed, n1 is dead simple to solve. It's just Q. Given n1 should return one solution. Now we can call our n queens function with 1, and then we expect to get let's put a result first. And then we expect to get a vector containing a vector containing just Q. Because it's a one-sized board, right? So we have one row, and that one row has one entry, which is just that queen spot, yeah? And this is failing because we haven't implemented our nQueens function. Cool. So that's a start. What would we want to return to get this to pass? Well, we'd want to just return the same thing we defined here. Maybe get rid of some of the spacing. Oh, no, not quite the same, actually, because the type is incorrect. This should be a string from Q, and then we're going to have to do that in the test as well, right? Oh, okay. So assert equals is happy to just take string slices and compare them to strings, I guess. That's pretty cool. Anyway. So, okay, we have a very simple proof of concept. Let's say we've passed the, or let's say implement n equals 1 case. Now, the next obvious case would be 2, right? And that's actually an interesting one because, like we said, 2 doesn't have a solution, so it should return no solutions. Now, what we'd expect there is an empty collection because there are no valid solutions to return. Oh yes, can't infer the type. What's the best way to solve that? Well, the simplest way to solve that is to actually define a type, which is going to be vec of usize, no, sorry, of string equals vec bang expected given in. Yep, okay, so it's failing now because it's returning what we specified before, which passes this test, but we actually expect it to be blank. So, if we were to try and pass this test, like I was sort of explaining before, if we were to try to pass this test, it would more or less solve the entire problem in just one step. But TDD allows us to move in small pieces, in small steps, small changes, right? We don't want to just jump in and solve the entire thing in one step. It isn't actually valuable, or it's not that it isn't valuable, but it's not as valuable as doing it in smaller steps. If we move in smaller steps, then we're able to see, okay, here's exactly how this particular piece here should work, and I can clearly define it and separate it. And more than that, it gives us the confidence of knowing that you have this particular part of the problem solved, right? If you solve the entire sort of thing in one step, then you might get part of the way through and realize, oh no, I've made a mistake and get into a confusing mess. But if you move in very small steps with tests at every step along the way, then you can always stop and revert and go back to the previous step. So the smaller your steps are, the better. It gives you more confidence. It gives you a bigger safety net. It gives you more room to experiment and change things because you know that no matter what, I can just go back to my previous step and I know that's tested and it's working and it's good code. So I don't want to use a test like this, an acceptance test, to solve this problem. So let's actually ignore this for the time being. Ignore second acceptance test, or ignore the second acceptance test. And then let's switch to doing this in more of a unit test style. So in more of a unit test style, yes, but also a inside out style, right? So inside out requires us to actually do a bit of upfront planning. We can't just drive it from the acceptance tests. We have to think ahead about what the solution is going to be. I have done this before, and I've done it in Rust before as well. So I know of a couple good tricks that should make this a bit more straightforward. But we'd have to think about what this is going to look like. And what we're going to have to do is use search. So there's really no way to solve this without searching. You can use declarative languages to not have to write the search yourself, but under the hood, they'll still be applying search algorithms. Ultimately, there's not really a way to solve this without performing a search. And if you don't know much about search algorithms, what that means in short is that we are going to look at every possible case, every possible board that could exist, and then find the ones that are valid solutions. Now, in this case, we want every possible solution. So we're just going to look at every single possible board we can. In other such problems, you might say, oh, I only want the first solution I come across, in which case you can be a bit more clever about it, because you can say, apply all sorts of efficiencies to avoid checking certain possibilities. You're only looking at the ones that really matter to you. But in this case, we just want to check everything. Now, what that's going to look like, I think, is something like this. So the number one trick to solving n queens is that, well, let's bring these back actually. The trick, I think, with any kind of problem like this is to look at your constraints and think about, given those constraints, what can I do to limit the search space? And one of the constraints you have here, that's kind of obvious if you think about it for a moment, is that you can never have a queen on the same column or row, right? Diagonal's a bit more complicated, but the column and row thing is particularly interesting because we could give each queen an XY coordinate. We could create an entire board in memory of these different cells, but we don't necessarily need to do that. The only information we actually need is where are the queens, and we know that each column can only have one queen. So we could say define just 4 variables to describe this whole thing. And of course, if you're using bitwise as well, you could probably get it down to just one variable, some bit masking operations. But let's, for the sake of simplicity, say, all right, we could have 4 variables, or, well, n, let's say, because of course the board could be bigger, n different variables defining where the queen is in each column. So for example, if we're 0 indexing it, this queen is in column 1. This is in, oh, sorry, it's in row 1 of column 0. So that would be 1, this would be 3, this would be 0, and this would be 2. So this is 0 because it's at position 0 of this column. This would be 2 because it's at 0, 1, 2 of this particular column. And doing it that way is going to make life a lot easier. We no longer need to check for the vertical rule at all. We don't need to verify whether another queen is vertically intersecting with this queen, because it's impossible. We just, by using a data structure like this, we make it completely impossible for that state to ever exist in the first place. So from here, we can say, all right, take, maybe it'll be easier if I scroll down a bit and do it down here. Take this board and lay the next queen. And the next queen can go in any of 4 different places. So we say from here, all right, if the queen were in this place, let's place the next queen in each of these 4 different places. And so each of these is a different board state, and we want to test each one to decide which ones are valid. And when we find something that's invalid, like this is clearly invalid because they're adjacent, so is this because they're diagonal, so is that because they're diagonal, all of these ones we can just, outright forget about them, because there's no point trying to explore these possibilities and see whether there's a valid solution, because we know that once we include these queens in any of these positions, the board is invalid. So there's no point going any further exploring those. But this one we know is valid because these 2 aren't intersecting. So from here, we can then go a bit further and try to figure out, okay, is there an actual valid solution further down here? Can we find another valid solution? And again, pretty quickly we can determine that these are invalid because they are adjacent to this one, And we've got, oh yeah, this one's invalid because it's in horizontal with the original queen. And then up here, this one's actually valid. So then you can explore this one further and say 1, 2, 3, 4, queen, 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 queen. We know that these are invalid and this is invalid, but actually this is the valid solution, or well, one of the two valid solutions to the n queens problem with a 4-sized board. So we've managed to search through all the possible board states, cutting off the ones that we're not interested in because we know they're invalid, and find a valid result. That fundamentally is how search problems work, and that's what this algorithm is going to be doing. But there's a few things we need in place that we need to plan up front in order for that to work. So we're going to need, what are we going to need? We're going to need a frontier. In a search algorithm, a frontier is a collection of the states you're aware of. So in this case, these are the boards. These are the boards you're aware of that need to be checked, you haven't yet checked. So it's a collection of sort of jobs to do effectively. We're going to need a frontier. We're going to need the actual search itself. We're going to need a way to tell if the board is valid. So this is sort of a utility function, you might call it. Is that quite the right phrase? I'm not sure it is. But anyway, let's call it validity, a validity function. Then we're going to need a way to actually convert that into the correct result, right? Because at the end of that, we're going to have to convert our data structure back to this format here. So we're going to want a way to create that format, serialize it, let's say. Yeah, okay. I think that's about everything we'll need. So the search part here will be responsible for adding new things to the frontier. Oh, and also, for that matter, adding things to the results, right? So it'll need to add things to the results. It'll need to search. It'll need a validity function. And then it'll need to serialize them afterwards. Okay, let's start with our data types. We talked about this before in terms of, placing a number for each column. So in this example, that would look like 1, 3, 0, 2. So this is one of the valid solutions, and it's just a collection of 4 numbers. So in terms of the results, what we'd want is, it makes more sense to start with a frontier, actually, for reasons that I'll explain shortly. So if you think about it in terms of a frontier, not every board is going to be complete, right? So you might want to say that it's a vec usize and start with an empty vector, right? But the frontier will sometimes include boards like this, where there is no, for these 2 columns, for these second 2 columns, there is no valid value you could put in there that would actually represent what is there, right? Because there's nothing there. So we need to use an optional here so that it can possibly be empty. And that's a lot easier to explain when it comes to defining the frontier, but let's also do that for a result. And then afterwards, we can convert the results to the format we see here. So, okay, this is something. validity function search. We're going to populate the frontier. I think we can test drive serialization and the validity function separately, and that'll give us our small steps. So let's say that we have a function. What do you want to start with, validity or serialize? Serialize is a neat one. Let's go with that. Our serialize function, and let's just say it takes one board. Yeah, let's say it takes one board, which is going to be like that. And this one board, it just wants to convert it into a vec of strings. Now, first thing we should do is get rid of that option. In fact, actually, let's just assume we do that outside of here. Because if you're getting a board at this point, if you're serializing it, then you know it must be complete, right? It wouldn't make any sense to try to serialize one that isn't complete. Unless maybe you want to do it for debugging, but I think we'll be fine. So we have this. Let's stick unimplemented in there just to stop the compiler from complaining. I probably should have mentioned this earlier. If it wasn't obvious, I have a test watch running here. So every time we save, it'll automatically run the tests. Now let's actually separate this into a different file, keep things simple. So we have a serialized file and a test module and a test. What's our first test going to be? Maybe we can do the same sort of thing we had before, go with the one size n. So given one size board serializes, the behavior is going to be the same every time. It's just going to be should serialize the board. So let's just say focus on the test case and call it one size board. Oh, I can't start with a, yeah. Okay, so our one size board is going to look like that, right? Yeah. It's defaulted to i32, but I think it will figure out that I want it to be a U size if we call serialize and pass it in. Yeah, there we go. Now it's a U size. And that results equals serialized board. Assert equals result should be vec containing Q. So this is the same as we can see here in the second example. Given a board of 1, the output should be just the letter Q, because there's nothing else really to define there. It's just a single cell. In this case, it's a double collection, of course, but in the context of a serialized function, we're just doing it for a single board, and then we'll sort of orchestrate that around multiple boards later. Now, let's see. Vec of Q. Okay, so this should fail. Yep, that's failing, not implemented. And simplest way to get it to pass, let's just say return vec. Oh yeah, getting that again. String from Q. Cool. So serialize one size board. It might seem a little bit silly to bother committing these single, hard-coded implementations, but it's a start. We have a function that can do one thing. It can solve one use case. That's a start. We can take it from there. Small steps. So let's say a two-size board can't be solved, and I don't think a three-size can either, so let's not bother with those. So let's take a four-size board, and solve that. Now that's going to be what we have over here, right? This is one of the two valid solutions for a 4-size board. That's 1302. And what we're going to expect out of that is essentially what we have over here, although it might also be this other solution. Which way around have we got it? 1, then 3. Okay, so it should be, yeah, no. Hang on. It's this one. It's the second one. Yeah, because 1 and 3, yeah, these are in the places we expect. We want to make this our test for the serialize function, or the expected value of our test, right? So we're passing in this successful completed 4-size board, and we expect this as the result. That'll line up a little bit better if we can just no, I didn't want to get rid of the entire line. It's just frustrating that doesn't quite line up to this. Just put a space there. Cargo format might just get rid of it later, but oh well, we'll try it. Okay, so now we can actually implement serializing this board, which is going to look something like, let's see, you want to go through each column, placing where the queens will go on which row in that column. Maybe, so there's two different ways of doing this, right? You could do it either column-based or row-based. You can go through each row and say, okay, given that the output, is going to be in the form of rows, it might make sense to do it row-based. Then you just flick through and say, okay, which of these has the row number that I'm on, and then figure out which index it has, and therefore know which column to put it on your row. Or the other way of doing it would be to create a whole blank board of dots and then go through each column one at a time and place them in the right place in the board. I don't think it matters too much which way we go, but I think the former one sounds a bit more sensible to me, less complex. You'd have to create the blank board to begin with. So let's say, no, we don't want to create a blank board. Let's say we are going to need some kind of board though. Let's say let board equal vecbang. That's going to have to be mutable. And then for index in board.len. So that basically means for n, it's for size of board. For I in n, we are going to do, want to select, hang on, if we iterate over the board, right, we're getting an iterator of all the items in the board, which is these numbers here. We can then select which one has the number that matches the row we're on, right? So we're effectively looping through the board, and let me make this a bit more obvious. We're going to be pushing one of these strings that will look like this, right? But we want to, and more specifically, it should actually be a string type. We want to I've also gone and given this, I've shadowed the variable name. Let's just call this result. But we want to make it the correct length for one thing, and we also want to add our Q in there at the right position. And we know what position Q is in based on the value. Hang on, so the right position Q is going to be in is maybe it's easier actually. Maybe it's more obvious if I change this to Y. That's really what this represents, right? We're going through it row by row. So if we start with this, that's Y0. That's looking at the first row. And then we're looking at the board where the representation is a bit different. We have a vector of U size, and each of these values represents that Y value as well. So we want to figure out which of these values matches Y. However, the value we then get out of that to decide where we're going to place our entry here is actually the index of where that position is in the collection. So we're going to need to enumerate the collection, and that'll give us a collection of tuples of the value and the index together. Then we can say filter. Which way round does it go? Does the index come first or does the value come first? Current iteration count as well as the next value. Iterative return yields. Okay, index comes first. So the index we can effectively call x because that's what it really represents, and then the value, well, the value is y, and we want to filter it down to where, oh yeah, it's going to need those because this is a closure. We're going to want to take xy and tell it what? Tell it to only give us the entries where, oh, I've overloaded y again. I've overloaded another variable, which this time is y. And that's going to be, what can we call this? YY, just keep it simple. Where these two values are equal, it might complain about the equality here because one of them is referenced and the other is not. Where they are equal, we then want to get that value out. Can we get it out by, yeah, last, right? Last and then unwrap, because there should only be one value anyway. So we just get that last value out and unwrap. And yeah, I thought as much. Can't compare them because one is a reference and the other is not. In fact, it's double referenced, which is a bit frustrating. Come to think of it, this should really be a reference to begin with anyway. And that's just going to complicate things more. Why is it double referenced? Iterate should turn it into a reference. It looks like enumerate has also turned into a reference again, so it's become double referenced. In any case, adding the double reference here has solved the problem for now. But I do wonder if this becomes a reference, is it then going to complain about expected a reference found vec? Oh, sorry, this is in the test, right? Yes. Oh, okay, no, it's fine with that being referenced. Okay, I did wonder if I might add another layer of referencing onto here, but no, it's fine. Okay, so that gets us the value back. Only it's going to give us the tuple, and we want just the first entry, which is going to be our x value, right? Yes, but the first entry is actually going to be .0, not .1. It's 0 indexed. So that's looking a little bit messy, but what I ultimately get out of it is our x. Okay. Now, result.push. So we now know, based on this x, which entry here should be the queen. However, something funny going on in our tests because it's getting a blank array, whereas I would expect it to. Yes, of course, because of the accidental shadowing I did earlier. It's got the wrong, it had the wrong variable there it was getting the length from. So now we're getting the actual board length, and yeah, okay, this is what I expected it to be doing. So we're basically returning a blank board instead of a queen, and we want to say, yeah, I think the best way to do this is to say, let's follow the same format we had here with this double Y thing, and actually rename this to double X, because we're going to need another X and we to avoid shadowing. I remember having a conversation with someone a while back, another developer, in which I explained that Rust supports shadowing variables, and he was like, why would you want that? It sounds horrible and confusing. And when you get into functions like this, you start to understand why. I'll give it to him as a fair point. It is rather confusing at times. It can cause you to make mistakes without really noticing you're making them. But it's also really helpful with ownership and borrowing to be able to do that. What's it complaining about here? Mismatched types, expected string found. Oh, okay, yeah. Oh, of course, yes. So what we can do here is say we really want to be adding chars onto the end of a string. So let's just create a blank string at the start of each of these, and then instead of pushing something new onto here, get the string out. In fact, we don't necessarily need to even do that, do we, actually? Maybe we can do... Oh, hang on. I've got to go. Be back in a moment. Alrighty, sorry for all the repeated interruptions. I just had a washing machine delivered. Very exciting for me. not necessarily so interesting for anyone watching. Okay, so we declare our row at the start here. Which needs to be mutable. And then we can push on to result. Now that should at least get us to the same place we were before, right? Where, yeah, in fact, better than we were before, because we're at least getting the right number of dots this time. So previously we were getting 4 empties where expected a queen, and now it's getting 1 empty and where expects a queen. And then all we have to do to get that to pass, I think, is to say if x is equal to xx, then row dot push a queen, else row dot push empty. There we go. Okay, cool. So implement serializing board. Potentially do a refactor here, but I think I'm mostly happy with this. This is a bit ugly, but it's not the end of the world. And I think it's pretty clear what's happening here. You go through the Y, so the variable names are really helping for the readability. We go through the Y, we're going through, that is, 1 row at a time. We create a new row. We get the X value for the queen in this row. Then we go through and place each tile, looking for where these match so we can place the queen. It's not too complicated, and the tests make it very obvious what's happening. Take that, convert it into that. Boom. Alrighty, that's end of part 1. So we've managed to go over the general theory of search algorithms and how we can visualize how this particular search problem can be solved. We've planned out a rough structure for how this whole function is going to work, where we're going to put our results, data types we're going to use. We're going to build this frontier of boards that need searching. We're going to write a search function that searches the frontier for valid solutions and populates the frontier with the next array of possible boards to be searched. And we're going to need a validity function to actually check whether or not these solutions are valid. We've also, in this session, implemented a serialized function that we can use to output our result. So in the next session, we will complete this validity function. So we'll be able to prove if the board is correct and implement the search function, which should bring everything together. See you then.